Recording in progress.
I think we're ready. Let's sharing screen recording. Got your hand out. This will take about 2 hours. Okay, so just settle in. I'm gonna go straight through. Okay. No break. Huh? Pretty much. Sure. And then Zoom attendees. Yep. Now, first thing, this is what the test looks like. Okay, so it's a booklet, standardized test. And the reason why I brought it in is really to mention the inside front cover. And on Zoom, you'll just have to, you'll see it when you come in. It is a test, 70 questions. 70 questions. And it's basically broke down half Gen Chem 2, half Gen Chem 1. Okay, and I'll do a little further, more detail of that in just a few minutes. But when you get the test, I'll have the equation sheet that you've seen. Well, you've seen a bunch, and I'll put them all together. And you also get equations from 151. Okay, and constants from 151. You got a periodic table. Basically, you'll get the Vespra chart, valence shell electron pair repulsion. The full thing. The full thing. Yeah. And I'll talk about that today a little bit. But on this guy, you get similar information. There's some equations, there's a periodic table, there's constants, but then, and you'll see it once you get it next week, up in the upper left-hand corner, there's a bunch of, it's like definition constants. Like, for example, they're using Na as Avogadro's constant. And they're using U as internal energy, if you want to see, but it's just a little key there for you. Okay, so that's a little reference for you for the booklet. Huh?
And so with that and the equation sheet, we'll just have those in our paper.
You can have 4 pages of notes.
Wow.
Okay.
So that's fine.
Yeah. How do we want to do this? 2 pages front and back, or 4 pages all front.
800 square feet.
800 square feet, yeah. We can be very specific. So you can bring in 1 sheet.
Sorry.
You can have a scroll.
Two given GTs and about a monster this morning. I'm gonna keep talking.
Don't do that before the test. Okay. Well, let's talk about material here. First off, still with the test, and I'm not going to rewrite that list. And actually, let me, I don't want to, can you all see it from there? And I'll post these notes, okay? And I'll post the video, right? But that's the real rough breakdown of the final exam.
That says chapter 8 and 9.
Yeah, I grouped those together just like I grouped 16 and 17 together, sort of in my own mind, because they're so closely related. Chapters 8 and 9. 8 deals with Lewis structures, and 9 deals with Vespra formula. So you never learn one without the other.
And you're recording this, right?
I am.
Okay.
Yes. And I will post that, well,
I
today,
know this is a stupid question.
tomorrow.
It's all the same book.
Say again?
It's all in the one book.
Yeah, Brown on the May. Yep. So the way to sort of interpret this information is, so you can say, like, what you see here, these are all the chapters that I found questions on the final exam. So one thing to notice, like chapter 1, it just hit me. I'm going to change something here. I'm going to add chapter 2. Yeah, let me do that. That makes me feel a little better. Like chapter 1, there's not something explicitly about, if you look at chapter 1, it's like, welcome to dimensional analysis, welcome to metric system. You use information from chapter 1 to do everything else, but there's not dedicated questions just on chapter 1. Does that make sense? I hope.
But we will.
Yeah. Well, you should know your basic metric to metric conversion, like 1,000 milliliters. If it is pints to gallons, I'll give you that. Okay, yeah, something like, or liters to metric, or liters to no, gallons to cubic meters. That's a fun one. Yeah. So anything really obscure like that, at least in my book, yeah, I'll give that to you. But let's get back to this. So what you're looking at when I say top 5 question or top 5 chapters, well, it's just that. These are the top 5 in terms of number of questions on the test that you see for 151. And then that's the top 5 for 152. Are there questions dealing with those chapters? Yes, but they're less important, just in terms of number of questions. Okay. Yeah, there's your 4 pages of notes, and there's no organic chemistry on the test. Okay, or at least nothing. I mean, could there be an organic structure that you use for chapter, I don't know, 16, something like that? Sure. But in terms of like, name this organic compound, no. What is this functional group? No, nothing like that. Okay. And as I've mentioned, I think you can take it either Monday or Tuesday. You don't need to let me know when you want to take it. Just show up. And I'll send out an email with, you know, more with the specific times, but, you know, probably, well, maybe I'll just do it right here too. Why not? So, time to take final exam. You can take it Monday, and really, let's say, you know, 8:30 a.m. up to well, oh God, the lab is, we're like 3:30. The whole day, I'm just going to be sitting in a room waiting for students, pretty much. Tuesday, not quite 8:30 a.m. 11. Oh, well, hell, it's not that much different. Let's just, no, I am going to give myself just a little bit of, not that, 10 a.m. to 42 p.m. Not that. Okay. If those times don't work for you, let me know, because there's still some flexibility. But it would have to be those 2 days. Like, you could come a little earlier on Tuesday if you needed to, but let's just make that sort of the official times. And I don't know where I'm going to be, right? It'll be somewhere on this floor. You'll just come find me. There'll be a note on my door letting you know which one it is. I mean, you can imagine it's like 312, 314, 303. Those are the top 3. Okay. And really, you can have as long as you want. If you come at 8:30, you can take till 3:30 if you really want to. I may just say no. I may just take it away from you, like, stop. Don't worry about it.
You passed.
You passed. I'll just come along and just put a big check. It's okay.
How much is that?
It is 15%. So it's a little bit more than a normal test. Okay. And it is curved. So basically, I mean, the curve is always sort of a little bit of a moving target, because grades aren't perfectly, I don't want to do that.
It's like standardized.
No, you know, if you plot, you know, the bell-shaped curve you always hear about with grades, and the middle should be around 75%. That's kind of what I shoot for. Right. So if because, you know, the average is not 75%. right? Because you're going to see material that's a little bit different than what you're used to. It's comprehensive over 2 semesters. It's a hard test, so the average may be 50. If the average is 50, then I'll add 25 points to everyone's grade, that kind of thing.
You get the 4 page.
You get the 4 pages. So typically what I see is that the grade you earn on the final exam is a little bit lower than your test average. So that means that if you're earning an 85 on the test average and you earn an 81 on the final exam, you still got your B. That's typically what you see, right? As I mentioned yesterday, where it really matters are the students that are like right on the borderline. If you need that extra, if you needed to get, your 88.7 up to an 89.5 to earn the A, then this is where you need to, really, well, you would need to make an A on the final probably, is my guess, just with not doing any real, serious math there. Just ballpark figure there in my head. Okay, we got some chemistry to talk about. Now, I'm really just going to talk about 151 material, since that's what we haven't talked about in this class, because you have 152 material. You have the test to review, you have the keys to the test, you have the test review notes, etc. What I want to do here is just run through some key concepts in General Chemistry 1 that it's not addressing any specific question that might be on the final exam, but the material here is just sort of the foundational information that you need to know to then be successful with the 151. And one thing, this should not be a surprise to you, right? You need to be able to calculate moles in a given problem. When in doubt, if you're dealing with some kind of stoichiometry calculation or anything, mass, moles, concentration, when in doubt, calculate moles, and that gets you at least one step closer. Now, why are there 4 different categories here? Well, there's 3 different phases of matter, and then we also deal with aqueous solution. Each one of those has a different way of calculating the number of moles from a sample. And so the first one, it's you're just going to be using the molar mass, and I'm kind of going to run through this quickly, okay? Like I said, it's recording, so you can watch it again if you want to. And I've included, just a little tidbit here. You should know sort of basic nomenclature for your salts. I would write in the polyatomics on your list, okay, unless you know them. And probably the periodic trend with respect to the charge on the ions, like calcium always has a +2, nitrate is that, and so that's the molecular formula. So you should have that little skill in your toolbox as well. And then once you have that, to calculate the molar mass, this thing comes in at 164 grams per mole. And right, how do we do that? And I'm not going to go through blah, 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 all the little steps, but right, there's 1 calcium, 2 nitrogens, and then 3 times 2, 6 oxygen. So there's an issue about interpretation of the molecular formula. And then you look at the periodic table, find those numbers, add them together, 164. Molar mass, what is it? It's basically, I think of it as a conversion factor. It tells me that if I go in the laboratory and I take this white solid and I measure out 164 grams on the balance, I am pretty much at 1 mole of that sample, or Avogadro's number of those molecules. Okay, so the purpose here, right, it's just calculation of the mole. And again, kind of quick here. Do you multiply? Do you divide by? 2 ways to do it. Just remember you divide by, or if you love dimensional analysis, then you should. I don't care. I do care, but I can't control everything. All right. I've given up on that. When I first started teaching, I tried to, no, now I'm like, that's okay. But it's a very useful tool, right? If I know that I want to keep moles and I want to get rid of grams, dimensional analysis says, oh, well, I need to divide by grams. All right, it's like Oh, in 151, I say it's a mathematical template to know how to set up the calculation. And you plug and chug, and surprise, you get a number, and it's the number of moles of that particular sample. Right, 2.5 grams is way less than 164, so you should anticipate it's much less than 1 mole, and it is. It's a very small fraction of a mole. Yeah, pretty typical. Yeah. You know, could a question, Jack, oh, 250 kilograms could be the same thing. You know, you convert it to grams and then go about your way. But yeah, this is usually typical amounts here. Now, the molar mass is also used for, right, so this was solid, and this one is a liquid. This is a pure liquid. Ethanol is a pure liquid. It's coming in at 115 liters. All right. And we are going to use the molar mass here because to calculate number of moles in a sample that's liquid, you're going to use the density value, the physical property of density there. Now, one thing to just to keep a heads up here, right? And this is true everywhere in any calculation. Make sure the units agree before you start plugging and chugging things along. So I have milliliters here. I want to convert that to milliliters. And this is probably the most useful conversion factor to know, 1,000 milliliters in 1 liter. And again, how do I know to put liters on the bottom and ultimately multiply by 1,000? It's because of dimensional analysis. Now I have 115,000 milliliters. Right. Same thing as moving the decimal 3 places to the right. That's another way to do this. So then once you have your volume in milliliters, and you're ready to go. You have, like I said, 115,000 milliliters. And again, do I multiply? Do I divide? Well, in this case, you're going to multiply by density because you want milliliters to cancel out. When you do that, now you're left with a problem just like the first problem. Now it's mass going to moles. And the molar mass for ethanol is 46.08 grams per mole. And so now if I divide by that, it gives me the correct answer, 1.97 times 10 to the 3 moles. You know, like this particular calculation with density, that's a chapter 2 topic. But I don't recall, like I said, I just don't recall a specific chapter 2. Could density show up? Sure, it could show up in a problem that's related to this kind of technique, this type of calculation, I should say. Yep. 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 So if I, all right, and you can move that, you know, multiply, divide by, flip it if you need to. If you flipped it, then you would be converting grams to milliliters. It's the opposite direction. Right. Oh, wow. There's also density is mass divided by volume. Anything that is something divided by something, you can do an equation triangle. Density is mass divided by volume. So then, you know, if I wanted to calculate mass, then that means density times volume. We use the equation triangle for molarity. Well, this semester, first saw it back in chapter 4.
I feel like I just draw the triangle.
Okay.
Like, and I use the 2 numbers, so D times D.
Okay. Oop, not that. Here we're dealing with gas. Our favorite equations for gases, you guessed it, ideal gas equation, sitting right there. And N is the number of moles here. So for the ideal gas equation, the most common form of R is that one, but there are a few others, and I don't know which one is used in the test, okay? But you're going to handle it all the same way. For example, if I look at my units, one problem I see is that the volume that's given for the sample is in milliliters. I want it in liters. And I'm just going to go ahead and convert that to liters. Okay. 254 liters. Just moving it 3 places over. I also see Kelvin, but Celsius is in the data that's given. Now, pretty much, yes, you have to do it here so the units agree, but in general, you always convert to Kelvin. There's a few examples where you don't, but it's not worth going through, honestly. Because even in those examples, if you converted to Kelvin, it would still work. Okay, just thinking about it. What's the equation? It's that guy. So 23 plus 273. That is something. It's 296 Kelvin. And then the last one, which we haven't seen in a while, is torr. And I'm going to go ahead and do that. What we know, and I'll give you these conversion factors if you need it. Pressure conversion factors will be given. We just got to know dimensional analysis. Oop, not that. Divide by torr cancels out. And that gives us a number, in this case, 0.901 atmosphere. And I'm almost ready to plug and chug, right? If I want to calculate N, I need to solve for N. So N is going to be equal to PV divided by R and T. And I'll just do the full plug and chug. 901, I'll even include units. Look at that. Yeah. So 0.901 atmosphere times 0.0254 liters divided by R, which is 0.08206. And that is liter atmosphere per mole per Kelvin. And then finally, what I say, temperature is 296. Unit analysis is very useful here. What's left over? Well, Kelvin and inverse Kelvin cancel out. Atmosphere on top, atmosphere on bottom, liters on top, liters on bottom. I'm left with inverse moles on the bottom. Well, what does that mean? That means, mole inverse. So essentially it just brings moles back to, on top, if you will. And you get 9.4 times 10 to the minus 4 moles there. And then the last main way that we see moles being calculated aqueous. We've done this before. We've dealt many times with a volume of a particular concentration of molarity. And we know that, and then just to do this, divided by liters, just like I said before. If I want moles, and it's moles, it's molarity times liter. And you can see that when you set it up. Molarity times liter. If I'm plugging and chugging, I'm going to go ahead, I would convert that to liters. But you know, the look of this 1128, instead of just putting capital M, what does capital M stand for? Moles per liter. And then if I multiply 55 or 0.055 liters, then what we see is we get a little amen. Yay, yes, you are doing it correctly. Okay. You know, if space aliens dropped down and they looked at this calculation, they had no, maybe they have no idea. MOL, what is all that? They see, oh yeah, that's cancels out. That makes sense. And if you're on an alien planet, you can also do the same thing. You know the math already. Let's hope. Let's hope it's the same math. It's got to be, right? Same constants of nature, no matter where we are in the galaxy or the universe. Unless extreme black hole, is that gonna? That would still, it's all the same rules. Who cares? Next. Okay, so we're not going to do about balancing equations. You should be proficient at this point. I will mention one little thing with this problem here. For an example like this guy, balance, that's not right, balance carbon last, because it is in its elemental form. Now, this is just a hint. This is just a helpful hint, guideline. It's not a hard, fast rule. If you started with carbon first, you would still get the right answer. It just may take a little longer and more frustration. And I'm sure there are examples where those little hints don't work out. Some other hints that's often talked about this when the topic is first brought up is that if an element is showing up in 2 or more compounds on the same side of an equation, that would be another one you would want to do last. Like, for example, that's not the case in this example. If you look at all the elements, they're only showing up in one place. You know, if I had chlorine here and I had chlorine there, then that would suggest I might want to do chlorine toward the end of my balancing act. And then the other little tidbit is all polyatomics, right, are balanced as a unit. Now for practice, again, I'm not going to do this, but I will give you the answer: 3, 3, 2, 3, if you're so inclined to practice on it later. Okay. I'm not going to do this one, but you can see, I mean, this is playing games with nomenclature and then balancing. The coefficients here would be 2, 1 on the reactant side, and then 2 and 1 for the mole coefficients on the product side. 2, like 2 nitrogens, 1 barium hydroxide, 2 waters and 1 barium nitrate. So if you want to practice that, you can do it. But I'm not going to do it because we got other things to worry about. But I will, if you have a question about it, because I know I'm just sort of rambling on at times.
I'm just trying to remember the
It's yeah. Now this one I will do. This is a limiting reactant calculation and a percent yield calculation. So the balanced equation is given. All right. And if you read the problem, it says nothing about what's the limiting reactant. Okay. It just says you have this mixture, and let me just sort of make some notes. You're mixing together 4.73 grams of the magnesium, 1.83 grams of water, and then you form 0.087 grams of hydrogen. Right, and all it asks for is what's the percent yield? Well, percent yield is actual yield divided by theoretical yield times 100%. Equation we given to you. Actual yield, well, that's what we're talking about here. That's the actual yield. So your job here is not just calculate percent yield. You have to recognize, oh, I need to figure out what the theoretical yield is for this thing. Yes.
And so since it's in grams, we don't need to convert for the theoretical.
So for the, once we get to the percent yield, yeah, we can just use mass for this example. Now, if we happen to calculate everything into moles, we could use moles, but grams is
So
traditionally used
this
here.
is not, I guess, unit of the equation or formula or whatever. 'Cause I know a lot of formulas we have to convert it to moles.
So for this one, there's like two aspects. So first off, mass is typically used for that. Now, what I'm getting ready to do, that's the one where you have to convert to moles and blah, blah, blah.
That's
So,
for the theoretical, I mean, that's
yeah.
for the limiting reactor.
Limiting reactant and theoretical yield. Yeah. So there's a couple approaches for figuring out the theoretical yield of a problem like this. The way I do it, for good or bad, is I do two separate theoretical yield calculations. Now, it's not the most efficient way to do it, all right? If you take, I don't know, I haven't taken the SAT in decades. GRE is a little bit fresher with that, even though that's been decades too. But, you know, some of those study guides will give you like little tricks in terms of messing around with the math. Okay, so this one I'm about to show you is not the most efficient way to do it, okay? But it does illustrate all the guts of the calculation. And this is a review, so the guts is not a bad idea. So we're going to do two separate theoretical yield calculations, and let's just sort of set the stage. That means that what I want to do is I want to take this value, pretend like it is the limiting reactant, calculate how much of the hydrogen that could be produced if all of the magnesium is used up. That'll be one possible theoretical yield. Yeah. Whichever one's smaller then is going to tell me which one is the limiting reactant. Okay. So
molar masses are rather similar, but grams are rather different.
that is correct. Yeah. Now that might be one of the tricks, but yeah, that might be one of the tricks that's shared like in a booklet or something, but let's go ahead. Yeah. Let's go ahead and take a look at the whole spiel here. So, right, when in doubt, you want to calculate number of moles. And since magnesium is just an atom, I'm just using the atomic mass of magnesium from the periodic table. Now, one thing between the magnesium and the hydrogen, it's just a 1-to-1 ratio, right? So you could leave out this next step mathematically, but I'm going to include it because we're doing a review and it's been a while since we've messed with this. We did something similar when we did titration calculations back in chapter 4. Right? If that first calculation gives me another number of moles of magnesium.
One thing I should mention.
Yeah.
Yeah, the first calculation gives you the number of moles of magnesium. Sort of let that imply.
Mm-hmm.
It might be helpful to have it explicitly
Mm-hmm.
written
Yep. So what you can see there is number of moles is left over, and that is associated with magnesium. And if you want to, you can also add Mg there. And then that prompts you, it's like, okay, well, then the coefficient for magnesium is going to go on the bottom, so it cancels out. Again, this is a 1-to-1 ratio. Numerically, it doesn't affect anything, but it does affect in terms of like dimensional analysis, blah, blah, blah. Hydrogen is H2, so it's not 1.01, it's 2.02. That's just for one hydrogen atom up there. It's not the elemental form. Why do I multiply? Well, it's because I want moles to cancel out. And then if I do the full plug and chug, which includes anything on the bottom I divide by, anything on top I multiply by, and I get a number, 393 grams. Now again, that's the theoretical yield if all of the magnesium reacts, and I didn't add this earlier, assuming water was the excess. I mean, that's what this calculation is telling me. All right. And then you repeat it. All right. You say, okay, now let me do the same set of calculations for water, but just using molar mass of water, molar coefficients. This step is going to be the same, the last one.
We only did that last step because we're trying to get it back into grams.
Back into grams, yeah. Yeah.
The actual.
That's true. Yeah. If we were just trying to figure out limiting reactant, we would not need, yeah.
Okay.
Yeah, we could just calculate moles and that would be just fine. Molar mass of water is that 18.02 grams. Now here, okay, so if we pause for a second and if we check out the coefficients, then it does matter now, okay? What's on bottom, what's on top? Well, all right, since we started with water, that's the moles of water. So the 2 moles of water is going to go on the bottom. So I want to divide by 2. And then 1 mole of hydrogen on top. All right, we're using the molar coefficients here in the dimensional analysis technique to transition from water to now hydrogen in terms of our math here. And like I said, the last step is the same because hydrogen is still hydrogen. And as Karen pointed out a few minutes ago, that is the smaller amount. And so now we can plug that into our theoretical yield to finally calculate the percent yield of what the thing is actually asking for, right? And so percent yield is equal to 0.087, how much we actually got, divided by how much we could have gotten if it went to completion, times 100%, 84%. Don't worry so much about sig figs on this test. Okay, there's not a question like, you know, 2 selections, 84 versus 84.1, you know, nothing like that. Yeah, and let me just make a note. Smallest amount is, well, it's theoretical yield, yes, but also it tells us which one is a limiting reactant. So now we know that is limiting reactant, and then this is in excess up there. Okay. Next topic are quantum numbers. Well, we'll get to quantum numbers eventually, but I want to go through like electronic configuration, orbital diagram, all that good stuff. Right? And to start off, let me use this periodic table here and just do the electronic, or let me do the orbital diagram for nitrogen as my first example. I'm not going to go through these questions and stuff like that because it's too drawn out. So let's talk about orbital diagram. So nitrogen is what we're going to do. And what we have to recognize is that there are 7 electrons, right? Sorry, electronic configuration, orbital diagram, that's telling us how the electrons are lying around the nucleus, okay? Because when we first learned this material Bohr atom, Bohr orbits. We have the nucleus. We have these different orbits running around, et cetera, et cetera. This first one is n equals 1, n equals 2. Guess what? N equals 3, et cetera, right, as we go out. Now, this is not reality. This is fine for hydrogen, 1 proton, 1 electron, and real simple stuff. The reality is we don't have orbits around the nucleus. We have orbitals. And that's where we get that. And I'll just do the full. Yeah, so 1s, 2s, and this is the sequence that you fill them up in. 3s, 3p, 4s. I'm just going to do a few of these, and 4p. That's enough for right now. I would probably recommend, and then there's more, etc. Put on notes. Yeah, that one entire 151. Yeah, I think I have the entire 151 set of videos and then a short list. Yeah. But I would put that sequence on the notes, right? That's where how the electrons are filled up as you start putting them into the orbitals. And I'll address this a little bit more in a second. But again, I kind of just want to get the orbital diagram down for nitrogen, just to remind you of what these things look like. And to get to nitrogen, you have to go up through 1, 2, 3 sublevels. Right? And we label those 1s, 2s, 2p. These are our sublevels. And then each individual sublevel has either 1, 3, 5, or 7 orbitals. So each line is an orbital. Right, that's a place for 2 electrons. And then we symbolize those 2 electrons with an arrow pointing up and an arrow pointing down. And we'll get back to why that is in a few minutes. There's a few rules that we have to keep track of. And I will talk about the rules after going through the orbital diagram. Right? So if I have 7 electrons to divvy out, 2 electrons per orbital. And if I start at low energy and go to high energy, and I count them up, 1, 2, 3, 4, 5, 6, 7. So remember, when for P, D's, and F sublevels where there's multiple orbitals, you put individual electrons in one at a time before pairing them up. The orbital diagram is the most information about the electronic structure around the nucleus. Before I do the electronic configuration, which is sort of an abbreviated, it's the same information just in a more compact form. And then you can take that and do an abbreviated form, and I'll do both of those. But let's just talk about the rules that we see here, okay? Now, one, I'm not gonna write it down. It's just something that should be pretty well ingrained. We start with low energy and we fill it up. That's sometimes referred to as an Aufbau principle. Aufbau? I don't know. It's close. That spelling is either correct or darn close. Okay. But more importantly, the other 2 rules. One, and I guess there's a couple ways to phrase this. One rule is called the Pauli exclusion principle. Based on spin, okay? Pretty much what this says, max of 2 electrons in an orbital. And then, yeah, we pair them up like that. One is what we say spin up. And then one is spin down. It's a quantum thing. I want to make it analogous to a magnetic field. Okay. Basically, and I'll come back to this in a few minutes. The pointing up, think of it like the north end of a magnet, and that's the south end of a magnet. So if you put it like that, north, and that's terrible. I should probably, oh, can I? No, there's one size for the laser pointer. North, south, north, south. What happens when you lie bar magnets like that together? They stick. Right? That's an attractive force that actually lowers the energy of the system. That's why the principle, Pauli exclusion principle is there. We will come back to spin up and spin down in just a few minutes. And then the other one to be familiar with is something called Hund's rule. And how did I phrase it the other day? Yeah, that's fine. Half fill orbitals before pairing up electrons. Again, which is what I did, right? When I filled up those 7, I did not go 1, 2, 3. That would be a violation of Hund's rule. That's actually a higher energy state than this. This, what we talk about here, this is the ground state. This is the lowest energy state for the system. Lyric, do you have a question?
Yeah. So with those two principles, like what you say is which rule?
The names are sometimes used on tests. Okay. So I'm not saying it's in there. It may not be.
Probably don't need to generate the names to be able to recognize them when you see them.
Yeah. Be able to recognize them. Because it's a multiple choice question, right? So it's not like an essay.
Well, it could be like which rules.
You should know that. You should know that's the Hund's rule. Yeah.
Because I know that that's the thing.
Yeah.
Not the name of the thing.
Yes. And that's common, right? That's one reason why I'm talking about this, because I guess memory is always a difficult thing to like really pin down, but I have a vague memory of like that being a common. Students know what to do. They just don't necessarily, well, that's the Pauli exclusion principle, and that's the Hund's rule, and that's off ball. And then you get on test, it talks about Hund's rule. And I'm like, oh crap, I didn't mention that. Anyway, so now I do it. This is the ground state. Yeah. So all of these are ground states. Yeah. So any deviation from this is an excited state, even if that means, right? Because why do we have all these rules? Because it points out the lowest energy configuration for the electrons. So any deviation, even, something like if on the 2s orbital, both of them were pointing up, that is a slightly excited state. Yeah, and it's absorbed the photons, probably radio frequency, something low end to cause that little flip.
Because like this is the reason you have spin up and spin down simply because you can't have electrons in the same position, in the same state.
That's a good point.
So like you can have your two first one's second.
That's a good point. I hadn't thought about that. So I'm not sure. But we will go. Any deviation for this is an excited state. Okay. But I'm going to look up the Pauli exclusion principle, see how makes sense though. Now, that's the orbital diagram. You probably also know and love the electronic configuration. So let's do that. Without much song and dance, 1s2, 2s2, 2p3. So these numbers up top, that's just the number of electrons, right? Number of electrons in each of those sublevels. Now, obviously, knowing your Hund's rule and given that information, then you would know that the ground state looks like that, unpaired electrons. Orbital diagram makes that information explicit, and the electronic configuration is more implied.
I remember you have some weird cases in the
Yes. If those energy states, yeah, like these early sublevels have big energy jumps.
Sometimes in 3D state will
Yep.
steal. I mean, sometimes the 3D shell will steal an electron from the rest shell.
Yeah, that's why.
Sometimes you just get a 4D electron early.
That's why you have that. That's why that 4s is before the 3D. Once you get to those higher energy states, the energy separation gets so shallow that it's actually more beneficial. It lowers the energy by adding the 2 electrons in the 4s before the 3D. And then on top of that, you know, we always draw the D sublevel like that, but in reality, and there's 2 on the bottom, 3 on top, or vice versa. So even that state can be switched around a lot of times. And then the energy separation,
The D sublevel itself has like sublevels.
there's a split to it. Yeah. Maybe not in all elements, but plenty enough to where you learn about it for like a month in inorganic chemistry. And then that energy separation oftentimes is equivalent to energy for visible light. So that's why like nickel is green and iron is yellow and copper is blue. Now, I'm going from 30 years back, so don't hold me. If you find something a little bit different on Google, let me know.
Because it absorbs certain frequencies.
And it can jump up and down.
Yeah, it's ground statements.
Yep. Oh, and then there is the not abbreviated electronic configuration. That's fine, but it's noble gas. Electronic configuration. And I'm just going to write it down here and then talk about it. Yep. Right, so what you're seeing is that that little set of 2 electrons can be represented by helium. Now, for something small like nitrogen, it really doesn't matter all that much whether you do the full or the abbreviated. It doesn't really, you know, make it any faster. But if you were doing something for like, if we pick on selenium for a minute, its electronic configuration is long. I won't write it out. But for the noble gas abbreviation, what you do is you backtrack on the periodic table, find the first noble gas. Argon in brackets is going to represent the first 18 electrons. And then after that, 4s2, 3d10, and I'll talk about where these are coming from in just a minute. And then 4p4 would be the top end of that. There's some disagreement with what I'm about to tell you here. So I'm going to stick with the well-behaved examples. when you see the abbreviated form, oftentimes we say that's the core electrons. There's like a divider here, and then these are valence. Long story short, the valence electrons react, core electrons do not. I always say, if you see a core electron reacting, you're not in this class, right? You're somewhere else. Now, maybe talk about electron capture from chapter 21. I think it's one of the core electrons that drops down into the nucleus, if I'm not mistaken, but I'm not a nuclear chemist, so yay me. So there's like sort of background, blah, 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 about the electronic configuration. Let's talk just a little bit more about this, the structure of the sublevel there, just a tad. Now, again, I'd recommend just writing it down, the list, that because you can find one. This is chapter 6. You can find one in chapter 6. Google it, you'll find it. There's, I'm sure, millions of images out there for this. But we can use our periodic table. And the way we say this is that this group over here, this is the S block. This little cluster, we also know them as transition metals. That's the D block. And then this little group, and I'm not going to include helium there, is the P block. And if we look at our sequence up here, notice that so every S sublevel starts at 1 and it has every single integer, right? P sublevel starts at 2. So basically you have to go up to n equals 1, n equals 2, n equals 3. At each one, you add another sublevel. So n equals 2, yes, that's what we say the principal quantum number, but also means there's 2 sublevels, 3 sublevels there, etc. And that's why the first D sublevel is the number 3D sublevel. Why is this useful? Well, it's not. No, it is. What it tells us is that 1s, 2s, 3s, 4s. If we can remember that this is the S, that's the D, and then that's the P, and then the bottom part, I doubt if that's going to be on the test. That's the F block. We're just not going to worry about those. And then we remember that, oh yeah, for the P block, it starts at 2P, 3P, 4P. Notice, right? Why did I say 4P4? I'm in the 4P sublevel, 1, 2, 3, 4 elements over. Where's the, when do we first see the D sublevel? 3D. D minus 1.
So I said D minus 1 to the whatever number you're.
That is a pattern.
That's what Fender told me.
Okay.
I was just trying to make sure that that.
It's just, I guess, another way to see the pattern. Yeah. But then once you've made your notes, if you will, on your periodic table, then, you know, for any given element, you just go up on the periodic table until you get to it. And basically, I mean, what are we doing? So again, just 1s, 2s, 2p, 3s. If I start a hydrogen, I go through the 1s, 2s, 2p, 3s, etc. So as you go through these different regions, as you go up an ascending atomic number, that basically sets up the sublevel pattern. Okay. How do I know there's 10 electrons? Well, because there's 1, 2, 10 elements on the D sublevel there. Each time I go up, scantium, titanium, blah, 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 I'm adding one more electron to the mix. Okay. Now, let's check my notes. Okay, let's talk about quantum numbers. And what I want to do here is I want to take this bit of information. I just want to expand it into an orbital diagram form so we can kind of see the guts of the setup here. So 4s, 2, 3, 4, 5, right? There's 5 orbitals on the D sublevels. So there's 5 lines, it's 3D, and then 1, 2, 3 on the 4P. Now, since part of this is just, instructional purposes, let me just, there are 16 electrons sitting there. Let me just add those 16 in as if I was following Pauli, Hund's, and Aufbau's principle exactly. And it would look something like, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, obviously, it's completely full, so it really doesn't matter how you fill it in. But if it wasn't completely full, that's how you would have filled it in. Okay. And then up here, 1, 2, 3, 4. Okay. Okay, so great. We have all those individual electrons in those different sublevels. And now I want to address quantum numbers. Quantum numbers, and I don't know how much you did with quantum numbers back in the day. But basically what it is, it's like an address. I mean, it's not an address, but let's see. I'll redo what I did yesterday, and I'll write this down. Each electron in an atom or ion has a unique set of quantum numbers. Okay? Each electron in an atom or ion has a unique set of quantum numbers. When a package is delivered here for me, it's 340 Victoria Road. It's not 340 Patton Avenue. There's a unique address for each of those electrons there. And the layout that I'm going to use here, I'm going to use the proper symbols. There's 4 of them, and they're given these symbols: N, L, M sub L, M sub S. I'm going to do the easiest ones first. The easiest is maybe N. That's just whatever numerical value you see. It tells us the principal energy level that that electron is housed at. The next one that I think is easiest is the spin quantum number. And there's 2 possibilities. If the arrow is pointing up, we label it +1/2. If the arrow is pointing down, -1/2. Getting back to the idea that each electron is going to have a unique set of quantum numbers. If you just think about 2 electrons in a given orbital, just say the 4s. Well, what we're going to see is that the first 3 quantum numbers are going to be the same. And then it's going to be the differences in the spin number that distinguishes one versus the other. Just like there are plenty of other addresses on Victoria Road. And the number indicates whether it's AB Tech or something else. Meals on Wheel. What about L and M sub L? Good question. Let's talk about L. Now for L, it is telling us which sublevel we're at. That's just the divider. Let's do a little table. We know our sublevels. S, P, D, and I'll go ahead and throw in F, even though I'm not sure F will even show up. If you are at the S sublevel, then L is going to be equal to 0. And then from there, it just goes up in integers. 2, 3, 0, 1, 2, 3. And if someday more elements are created, yeah, I guess, oh boy, that'd take a bunch. G maybe would be the next one. A new sublevel. It would. It would. It would. All right. So, and we'll put it all together in a few minutes. But before we do that, all 10 electrons in the 3D sublevel, they all have an L number of 2. Finally, it is this one here, M sub L. That's the one that actually designates, it shows us, or let's say designates the specific orbital. And I'm just going to write in the numbers first. So 0, and then over here on the 3D, it starts at -2, -1, 0, +1, +2. In the P sublevels, it starts at -1, -1, 0, +1. Let's just pick it apart a little bit. These are not random numbers. And let's just mess around with the D for a second. I said if you're on the D sublevel, then the L number is equal to 2. Well, notice there is a corresponding pattern here. What's on the bookends of the individual orbitals there? Well, it's just the -L up to the +L. I said L for a P sublevel is 1. Well, -L up to +L. So the -L and +L like bookmarks, and then whatever the whole numbers are in the middle, then it just laid out in that fashion. So now let's just pick one and see what we can figure out about it. Let's just pick that electron. And we want to do the full set of quantum numbers. For F, yeah, so F would start, it would be -3, -2, up to +3. And that would generate 7 different orbitals, 2 electrons in each, 14 electrons. I don't have my laser pointer, but that's why there's 14 elements on that bottom block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14.
I know, but I'm saying between the numbers of -3.
There's 7 orbitals. So 2 electrons per orbital. That's where I got the 14.
I'm talking about the ML. How it goes from negative to the +2 for F is -3 to +2.
So let's say 4F.
Oh, it's 7. That makes sense because you're just doing the -3 and the +3.
Good.
Okay.
Good. Great. that one electron I highlighted. All right, N's no problem. That's just 3. M sub S is no problem. It's just pointing down, so it's -1/2. And now that we know the guts of the L's and the M sub L's, then we know that the D sublevel is at 2. And then since it's in the 4th orbital, then we give it the +1 value. Okay. Notice that we'll do one that's not allowed. You could not have like 3, 2, -3, -1/2, something like that. Certain patterns that are not allowed in a sequence like this. Right, so by knowing that, okay, so the bookends for any sublevel has to be plus or minus the L. If I come across this, plus or minus of the L, well, that's -2 plus 2. That's the maximum N. I can't go any farther on either side of that. So something like that is not allowed. It's always going to be that order. Yep. N, L, M sub L, M sub S. Yeah. So then you get questions like this thing. Which quantum numbers are possible? And let's see. One thing I want to point out is that I got to be sure. I haven't taught 151 in years, so just let me pause for a second and make sure. Yeah. One thing to note is that N is always greater than, shoot, that's not wrong, L. That's a true statement. So like if you look at this list, just looking at those first 2 numbers, oh, that one doesn't work. That one doesn't work. Also, something that usually pops up is your S orbital. You know, N and M sub S can vary, but in the middle it's always 0, 0. And maybe I should say that if L equal to 0, then M sub L is equal to 0. So that would tell me that that's a big no-no.
So that
Cannot be.
oh, it has to be.
Yeah. Yeah, because like the 0, the 0 for S, I mean, for 0 for L tells us we're at an S orbital, right? 1, where's 1 show up for the M sub L? Well, 1 is only associated with either P or D or F, right? It's always something bigger. So you get little questions like that as well. And I think those are probably the main patterns that you see. And then this question is what I just did here, just with a different example. Okay, unless there's questions, I want to move on to Lewis structures, Vesper formulas. And again, the purpose of this is not to cover every single topic in Gen Chem 1, just to lay down a foundation the best I can, and you know, without going on for a week. And so this topic, that's chapters 8 and 9, which 8 is associated with Lewis structures, and then 9 is the valence shell electron pair repulsion, which is essentially geometries. Now, when we did the organic chemistry spiel, I did use the term Lewis structure. A structural formula is essentially a Lewis structure. Now, the way Lewis structure is generally used for Gen Chem 1 is that you have some, I won't write this down yet. You have some central atom, and then things are attached to it. And there's just one thing attached. That's typically what you see. And that's the way I'm going to treat it here. But essentially, I mean, we're building up these structural formulas. And I wanted to use this as an example. This is formaldehyde, embalming fluid. It covers a lot of bases, a lot of topics here. So we're going to deal with valence electrons, octet rule, and formal charges for this guy. And then apply it to the VSEPR formula. And first step, there's actually one or two could be first step, it really doesn't matter. But let's just talk about the central atom. And let me just give the central atom for this one, and then I'll discuss what's happening here. Carbon is the central atom for this guy. Again, in a very sort of narrow framework of structural formulas in terms of Lewis structures for 151, it does this. Is there's just one central atom, then everything else is laid out around it. And usually I just lay it out in just a symmetrical fashion. It doesn't really matter too much. And some of the rules here, it's not going to be hydrogen. Hydrogen is small, there's not much going on. There's just one s orbital, one electron. It can only do one bond. It's very, very boring, okay? And then after that, you're going to see it's usually the first single atom, which in this case, the first single atom is your carbon in that formula. And that's why I put it in the middle. The next thing you want to do is valence electrons. I'm going to go back to the periodic table just a few pages back and talk about the valence electrons. It is a periodic trend. There we go. Valence electrons are what's used in chemical reactions. The valence electron is actually 1, 2, 3. It's just a Roman numeral that's assigned to each of those families. 1, 2 electrons, 3 electrons, 4, 5, 6, 7, and not helium, but on neon, 8. I doubt if you'll see a noble gas on the test. Neon doesn't bond to anything, but you can get argon, krypton, and these other ones to actually form some bonds, but you have to sort of beat the heck out of them. So what are the atoms that we saw in the last? We have hydrogen, we have carbon, we have oxygen. So 1, 4, and 6. Okie doke. Let me just rewrite this thing. H2CO. There's one valence electron for each of the hydrogens. There are 4 valence electrons for the carbon, and there are 6 valence electrons for the oxygen, for a total of 12 valence electrons. And these are what's going to be used to build the molecule. All right, they're going to be used for bonds and lone electrons. And I'm just going to say lone electron pairs. You can have examples where you have individual electrons, but the lone pairs are more common. Okay, so first off, let's just say, okay, what are our bonds? Well, we know we have to connect everything together, so let's do that. You start off generally with just one bond to each of the atoms just to connect, get things going. And then you bring in octet rules. Now, I'm talking as if I'm teaching this for the first time, all right? So if you're looking at this like carbon needs 4, yes, those are coming from the octet rule. So let's talk about that. So the octet rule just tells us the number of electrons that are going to be around a given atom. And usually we talk about hydrogen and boron and aluminum together. And then the most important one is this group: carbon, nitrogen, oxygen, and fluorine, and really anything else on the periodic table. 2, 6, 8. Now this little group here, that's definitely at max of 8 electrons. They're fairly small. There's only so much real estate around carbon, nitrogen, etc. And then the orbitals prevent it from forming any, further bonding. But then there's another group, and I'm just going to say sulfur, phosphorus, etc. 8 or more. Sulfur and phosphorus are often the most common ones. These are the ones that can expand their octet. And I should have brought my laser pointer, but oh well, up here. Here we go. I do have a laser pointer, right? So this row here, max, and really it's just maxes out at 8 because there's only so much space around them. But from there down, you can get 8 or more. You can expand the octet. Now, again, typically chlorine, yeah, sometimes thrown in, but usually it's just phosphorus and sulfur are the most common ones. And actually, these don't even form covalent bonds, at least ones we got to worry about. So then with that in mind, what we do is we use our octet to decide how we divvy out the remaining electrons. So what I mean by that, well, the leftover electrons, it's the valence electrons minus electrons used equals leftover electrons. 12 minus 6 have been used. We have 6 left over, or remaining, however you want to say it. Unused. Yeah. So like these 6, the 6 used would be those 6 that were used to connect everything together. The ones that are left over, you use your octet rule and you decide, well, they're going to be pi bonds and or, depends, lone electron pairs. Now, if I think about my octet rule, notice, so hydrogen, always 2 electrons around each of the hydrogen. You can't do anything with these 2 bonds. This region cannot change, is what I'm trying to say. But then if I look at carbon, there's only 6 there, right? 2 electrons per bond. There's 2 options. I could put a lone electron pair on that carbon. That would satisfy the octet rule. Be a little weird. But then more traditionally, it's a pi bond there. Yes?
Aren't you, is there a rule for what shells are supposed to pull first? It's supposed to start with the non-central atoms or something? I don't know if that's right. I think I remember there's something.
Let me think. Could you be thinking about just the electronic configuration in terms of filling? Now, it could be, there might be, I don't talk about this, but I guess there's some benefit of maybe getting the octet of the central atom filled first. That might be it. I wouldn't be surprised if an instructor talked about that, because that would be, maybe I should start talking about the next time I teach 151, but that would be convenient, because then it starts like this. Okay, so let me do these in orange. You know, if I put a pi bond there, that would give an octet of 8 for the carbon. It's satisfied. And then the only thing that's left to do is like, you know, oxygen. How would you satisfy oxygen? Well, obviously that's going to be the most popular way. Could I do that? Could not. Yeah. So that this one has 1, 2, 3, 4, 5 bonds. You'd say you'd just violated it. Oh yeah, yeah. Octet. Well, the octet for the carbon would be satisfied for that, but the carbon would be. If I had done, like if I put it, it's not pretty. It's what we're trying to say here. Right, so that molecule, this is the correct Lewis structure. You get to just using the octet rules. Okay. Now, I don't want to stop there, because there's always now formal charge. These are useful for more complicated ones, but all molecules will follow these rules. One thing to do is that you can do a formal charge on each atom. So that's one thing to note. The formula for the formal charge is going to be equal to the valence electrons, and there's a little variation of this formula. They all come up with the same answer, okay? Number minus the number of bonds minus the number of lone electrons. In 151, I used to say valence electrons minus the number of lines minus the number of dots, because that's essentially what you're doing. And let's just apply this to each one. So since, do I need a different color? Sure. Let's do this in blue. So both of these hydrogens are identical, meaning there's one bond. That's what hydrogen does. Formal charge, valence electron count of 1, minus 1 bond, minus 0 lone electron pairs, has a formal charge of 0. Think of the formal charge as the actual charge on that atom. Carbon, a valence electron count of 4, 4 bonds. So I'm talking 1, 2, 3, 4 bonds. So actual, like I said, the number of lines around that atom. 0 dots, formal charge is 0. That's good. Oxygen, 6 valence electrons minus 2 bonds minus 4 dots, or 4 lone electrons. That's equal to 0. That's good. Yay. This is not unusual, especially for a molecule that's not carrying a charge anyway. Now, sometimes you do get -1 and +1 in a molecule like that. But then it comes to the last rule here, just to be aware of. Sum of formal charge needs to equal the overall charge. And we're good. All right. 0 plus 0 plus 0 equals 0, which is the original charge that we started with. Now, there is actually another Lewis structure for this. Actually, there's a few. We're looking at resonance structures. If you go through your formal charge calculations here, hydrogen's still 0. But this carbon, 4 minus 3 minus 0, it's actually carrying a +1 charge. That's not good. Oxygen, 6 valence electrons, as always. We got 1 bond around it now, and now we have 6 dots. And so now it's carrying a -1. Typically, when you find this, you actually apply those charges beside those atoms. And I mean, it looks different. We've actually violated. No, we haven't violated. Right? I said maximum of 8 electrons. I said nothing about fewer than 8 electrons. So octet rule is fine for a molecule like this.
Also, the oxygen is what's it up to? It looks like it might have 9 electrons.
No, it's so 2, 3, 4, 5, 6, 7, 8. So it's okay as well.
Okay.
Yeah. So in a technical sense, we haven't violated any octet rules there. And then this guy is just fine. You know, these are 0. +1 minus 1 gives us 0, which again is the original overall charge. So just be aware. There's some little variation on Lewis structures there.
So in order for it
Resonance. Yeah, so
it has to equal the overall charge has to equal, it has to follow the
yeah. Yeah. So basically the way I say this typically like in a 151 class, if you've gone through all of these rules and they're all satisfied, that's a legitimate Lewis structure. And then if they look different, like these two, then you're looking at resonance structures. That's essentially what you see here. And not to drive you crazy, that's another one. That one's carrying a minus charge and that one's carrying a positive charge. I still got 12 electrons. 2, 4, 6, 8, 10, 12.
back to
Well, so determining factor. So the one you would use would be, there's a few rules that you can apply to this. For an example like this, which is fairly typical, if there is, you know, if it's a molecule with 0 overall charge, the structure where there's no charge, no formal charges is best. And any deviation from that are not good structures. We call these minor contributors, and this would be the major contributor. I don't think it's too important.
Somewhere that there's like a specific name for molecules that explicitly do not have a form that has no positive or negative charge on it. Like it's
That guy?
it's typically like the molecules that don't have that form typically have like a plus charge on one side and then really far away at minus charge.
Could charge separation?
Yeah, and they're all just sort of,
Does that sound familiar?
it's
Okay.
it's not this one.
Yeah, it's not. But yeah, I usually say chart separation with something like this. One more topic. Let me just do a quick little song and dance / intro for valence shell electron pair repulsion. And I'm going to use formaldehyde again. Again, it illustrates a couple points pretty well. And you know, the chart will be given to you. Well, the formula, see if this looks familiar. And I'm using the N and M, that's my own. AXE, Vesper formula. So A is just the central atom, A for atom. That's not very important. A is always there. The X, that's the number of bonding domains or regions, depending on the preference. And then E represents the number of non-bonding regions. And again, this is specifically around the central atom only. And for example, if we want to talk about X, what is X on this? So I see one region where there's bonds. I see another region where there's bonds. I see two bonds going to oxygen, but that is included as a single region. So for this one, it's AX3. And notice, I mean, if I'm looking for non-bonding regions around the central atom, it's 0. So I just leave E off. EX3. I'll leave it as A. Yeah, that's usually what you see on the chart, at least the one we use. I'll put it that way. So yes, there's some lone electron pairs up there, but that's not on the central atom, so we don't count it. Okay. It's the shape, it's these things around the central atom that dictate the overall geometry. And then if you look at, if you then go dig out a Vespra chart, and I'll just write a little bit down here. You have the formula, and you have overall geometry, and then you have molecular geometry. And for the AX2, or yeah, there is an AX2. AX2 would be linear. You're thinking AX2E2. Yeah.
That's what I was.
Yeah. If you looked at the AX3, like this example, you would see trigonal planar for both of these geometries.
And it's two would be two double bonds.
Yeah. Or you could have a
Or
single bond. Yeah. So great. They have the same name. Trigonal planar, just sort of, it's the triangle, if you will. And these atoms are actually in the same plane, the plane of the paper there. Oh, so overall geometry, well, that's just sort of overall, you know, what's that includes, we'll say everything around the central atom. And I'll just say A. And then this one, molecular geometry, which is the one that I find most useful. That is the shape of the atoms.
So,
Yeah, you could also have the trigonal bipyramidal and octahedral. I would be surprised if those were on the test.
Those require more bonds.
Yeah. And I'll give you all of those on the test, okay? Now, let's look at a quick example where the overall and molecular geometries are different, and I'll just use H2O. H2O is this. And there are two lone electron pairs on oxygen. And if I go in, think about X, what color? Yeah, use red. Let's use red again. There's two regions where you see bonds. Okay, so that's that's a big 2 for X. Yep. And then, right, yeah, non-bonding regions. There's one region, lone pair electron, another region, lone pair electron. It is. Yeah, if you actually look at, it's like Mickey Mouse ears on the oxygen there. So AX2E2. If you go dig out the chart, AX2E2 says that the overall geometry is tetrahedral, bent. You may see V-shaped. That molecular geometry is trying to tell us, what do the atoms look like? V. Yeah. Yeah. Whereas tetrahedral, tetra for 4, it's actually, you know, 3-dimensional shape with 109.5 degree bond angles, all that good stuff. But there's 1, 2, 3, 4 things around, total around that oxygen atom. Oh, the bond angles are not on the chart. You will not. Yo, you probably write it on your paper. Write it down on the cheat sheet. Yeah, it's probably. I don't.
Exact bond angles depend on which atoms would be bonded.
Yeah, and we will. I think idealized bond angles is probably what I'd recommend
Do
writing
you
down.
think that you can pull it up real quick?
Yeah. Let's see.
I tried to see if there was one on Google, but it's, I think all the stuff you have posted is videos.
And valence shell, electron pair, repulsion. Let's give it a shot. Let's just click on one. That's not, oh, well, that's pretty good. Like on this one, I can't really point to it. I don't think, yeah. You know, it shows you the deviation as lone pair electrons are added to it, but it does show you the idealized form of the angles. That's probably the complete, that's not given. Ah, okay. But I'd probably jot the bond angles down on your cheat sheet. The main ones are these top ones, 180 degrees for linear, 120 for trigonal planar, and then 109.5 for tetrahedral. And then as lone pair electrons, you can see it here, as lone pair electrons are added, again, I can't write on the screen, but the angle reduces just a little bit. So like going back to this guy here, the idealized bond angle down here would have been 109.5 degree bond angle. But these lone pair electrons, they take up so much space that it actually pushes down on that angle. And so squeezes that a little bit lower. So like here, this bond angle is less than 109.5 degrees.
We need to know the shape of the different pimples. Like, I remember touching on this shape.
Yeah, that's probably wouldn't be a bad idea. I mean, I don't know how much time to spend on that. Yeah. Yeah. S is spherical. The P has the 2 lobes. D's are mainly 4 lobes, but there's also one or at least one that's a bit of an oddball. Yeah. F, I wouldn't worry about F's. It's just a torus, like a belt.
Like all that stuff was on the one. This is just trying to raise the topic.
Yeah, that's why I'm sort of like, it could be like, I would be, well, I can tell you, I mean, just a question, what's the shape of an S orbital being spherical? I would think that would be too easy for that thing, that kind of test. Yeah, at some point, sort of have to use your own judgment. Look at the dynamic study modules that are posted, what, next Tuesday or whatever, right? All of those are extra credit, but you can just start working some of those for just a basic review of the material. I think that's a pretty, and you know, base your time. That's one reason I'm giving you that. I mean, I want you to know what's on the test and what's not on the test. And by doing that, I'm emphasizing, you know, those 10, still it's a huge topic, right? The dynamic study modules that's already gone, it's in the past, you can go back and practice with those. It won't add any points to it now, but you can go back and practice. And for that matter, you could go back and practice any of those assignments. You still get 4 attempts to complete the homework assignments. Dynamic study modules don't work that way, but homework assignments do.
And you said that last one.
All of those are extra credit. Yeah. I'd probably so, yeah. I mean, what I did today is a decent foundation. But yes, I missed a lot. That is true. Like I didn't do anything with gas law. Well, I did do the PV equals NRT
I feel
calculation.
like that's a good review. That was
Yeah.
a really good review.
Because realistically, I mean, could we go longer? Why, sure.
For 10 days.
Yeah. A whole semester we could talk about 151. But
I feel like 151 was so packed that I was coming and I would leave the lab with a panic attack and go to these land by.
oh no.
I can't do it. Because it was just so much. It's like, here's all this stuff. Have to see it 12 more times.
But I think with that, we'll end it for today. You know, if any kind of questions pop up in your studies, let me know. Send me an email.